Hi everyone. Today we are going to get into a very important diagram, which is called the HR diagram. So now that we know a little bit about stars and the difference between stars, we can look at one of the most important charts in all of this class. So we're going to be able to read and also interpret the HR diagram and all of the things that it's telling us, as well as look at binary systems and the relationship between mass and luminosity. So before I show the HR diagram, I'd like to give an example using cars. So this is a little similar to what the HR diagram looks like for stars, but here we're thinking about cars and the weight and the power, the horsepower of cars. So on the bottom of this graph, we have weight from heavy to light. So a really heavy car versus a really light car. On the y-axis, we have horsepower. So low horsepower and high horsepower. So how do these things relate for cars? So if we were to plot all of the cars on this graph based on the weight and the horsepower of a car, we would have generally most cars that have a higher weight also have a higher horsepower. So in order to have a higher horsepower car, it's going to be heavier. If you have a lower horsepower car, it's going to be lighter. So my Mazda 3, for example, base model, it's going to be down here. It's pretty light, not a lot of horsepower. Most cars are going to fit in this general, what we call main sequence of light cars have low horsepower, up to high cars have high horsepower. So the normal cars are what we call the main sequence. However, there are some that differ from this main sequence. We have the economy models, which might be a little heavier even though they have lower horsepower. Then we also have sports cars and racing cars. So our sports cars are going to have a higher horsepower, but be lighter, especially the racing cars. They're going to have almost the highest horsepower, but they're going to be very, very light in order to be successful at racing. So most normal cars fall on our main sequence. But there are some special cases that are outside of the main sequence because they don't fit that exact main sequence. So this is very, very similar to stars. So this is called the HR diagram, named after the two scientists that came up with it. So on the bottom, instead of weight for your car, we have temperature. So the bottom is temperature, and you'll notice on the top is also spectral type, because we know that the spectral classes correlate directly to temperature. So O boy and F grade kills me. The spectral types there, the O is the warmest temperature, so that star is going to look blue. The M is the coolest temperature, so that is going to be more red. And then along the y-axis, we have luminosity, so the brightness compared to the brightness of our sun. So you'll notice that a luminosity of 1 means that the star is just as bright as our sun. So our sun here is plotted at the temperature of our sun and the luminosity of the sun being 1. So the stars above the sun are brighter than the sun, the stars below are cooler. So this graph allows us to sort stars based on temperature and brightness. So here we have our main sequence of stars, where we have the hotter stars are brighter, and we have the cooler stars are less bright. So the cooler stars are going to be more red, they're less bright. That is our main sequence. That's the normal. That's the average. Most stars follow this pattern, where if they're cooler, they're less bright. As we look at warmer stars, hotter stars, more blue stars, they're going to be brighter. So our sun falls right on that main sequence. But you'll notice there are some outside of the main sequence, just like we had for the cars. So when we're looking at the HR diagram, we say that a star is located in a certain space on this diagram, But it's really important to recognize that that doesn't have anything to do with where the star is in space. So we're only talking about where it falls on this diagram, looking at the qualities of the star. We're not talking about its actual location in space. And it's also important to note that stars move as they age. They don't move in space. They move on this diagram. So a star will actually move and cycle around as it ages because it's going to change in brightness and change in temperature. We're going to get a lot more into this next week. So we have our main sequence stars. These are about 80% of all stars. So almost all of the stars in the universe fit on this main sequence, where if they are cooler, they're less bright. If they're hotter, they're more bright. But we do have some outliers. So here we have cooler stars. They're more red, but they're very bright. So they're not on this main sequence. They're not following this regular normal path. They're brighter, even though they're cooler. So how can that be? How can a star that's cooler be extra bright? It must be huge. So these are what we call giant stars. So it's cooler, but it's huge. It's 10 to 100 times larger than the sun. It must have a very large surface area in order for it to be as bright as much hotter stars. So here we have our giant stars, and then we also have up here our supergiant stars. So they're very cool, but they're incredibly bright. So these stars are upwards of 1,000 times larger than the sun. They are gigantic. So they might not be all that warm. They might not be very hot, but they're huge. So they're still very, very bright. So the stars here on our main sequence at the bottom, the coolest stars on our main sequence are called red dwarfs. These are actually the most common stars in the sky. So they're small, they're very cool, and they're right on our main sequence. They have low luminosity, but they're cold. They're cool. But you'll notice here we also have some very bright, some very warm, but not as bright stars. So these we call white dwarfs. So they're teeny tiny, but they're very, very hot. So they're very, very hot, but they're so small that they're not going to output all that much light. So they aren't going to be very bright because they are so small, even though they're really, really quite warm. So they're just as bright as these cooler stars because they are so small. Yes, they're hotter, but they're so small that the brightness is much, much less. So, thinking about size, we can add to this diagram. So here we still have our temperature, the spectral type that goes right along with it. We have the luminosity. Then we also have the apparent visual magnitude, which is matching up with the luminosity. So what we can do is we can add lines of radius. So lines of constant radius. These are the dashed black lines. So here, we use solar radius, meaning we compare everything to the size of the sun. So on this line here, any star that were to fall right along this line where it says every star on this line is 1 solar radius. It means any star on this line is going to be the exact same radius as our sun. Notice that our sun falls perfectly on that line. So anything on this line here is going to be about a tenth the size of our sun. So here is a red dwarf. It's about a tenth the size. If we go up, we can see this line here. All of the stars that would fall right on this dashed line are going to be 10 times the size of our sun. So you'll notice that the white dwarfs over here are teeny tiny. They're very, very small. And that our supergiants, here's Betelgeuse, those are 1,000 times the size of our sun. They're huge. They're absolutely super giants. So looking at this HR diagram, we're also able to look at the size of our sun when we, the size of the star when we add these radius dashed lines here. So you'll notice that most of the stars on the main sequence are similar in size. So it goes from a little bit smaller than the sun up to about 10 times the size of the sun. But most of the main sequence is, they're similar in size. Not the case, of course, for our white dwarfs and our giants and our supergiants. So we can also use a star's spectrum to determine the size of the star. So a larger star is going to have a less dense atmosphere because it will have a larger surface area. So the larger star will have a less dense atmosphere. There's not going to be as many gases in the atmosphere. This means that the spectral lines that we see will be quite thin because the absorption is going to be less because there's less atmosphere. So there's less gases in the atmosphere doing the absorbing. So there's going to be less absorption. So for a supergiant, for example, we would still see the same spectral lines, but they're going to be much thinner. For a smaller star, so let's take a main sequence star, this is going to have a much thicker atmosphere. That means there's going to be enhanced absorption of the gases in the atmosphere. So the lines on the main sequence, the lines on the spectrum are going to be much thicker. So a supergiant is going to have very thin lines. A main sequence star is going to have very thicker lines. So looking just at the star's spectrum, we can actually tell something about the size of the star. So then we can separate our star into classes based on spectra. So here we have these classes. It goes from a luminous supergiant to supergiant, a luminous giant to a giant, a subgiant, which is a not quite as large giant, and then main sequence. So when you're talking about a star, you would describe the star with its spectral type. So the, oh boy, an F grade kills me. And then the class of luminosity. So our sun, for example, is a G2 5. So it's a G2 spectral type and a 5 because it's on the main sequence. So we talked a bit about stars that are too distant to measure their parallax. And they're too distant for us to be able to accurately measure their parallax. But this is a very powerful chart here. So if the star is too distant to measure the parallax, meaning we can't figure out how far away it is, but we know everything else about it, we can find its distance using this HR diagram. So we can take its spectral type, up here, a luminosity class, and its apparent magnitude to determine the distance away from the star. So this is called spectroscopic parallax, where we use the star's location on this diagram to tell us more about the star. So, for example, we can use the star's, let's say we're looking at a star, is too far away to determine its distance because we can't determine its parallax with any confidence. So we can use its spectrum to tell us its spectral class. So we know where it would fall here in terms of temperature. We can use the width of the spectral lines to tell us its luminosity class. So now we know where it falls here in luminosity. So we can plot the star on our HR diagram using the spectral class and the luminosity. From there, we know its absolute magnitude because the absolute magnitude is also plotted. So we would know where it falls on absolute magnitude. Then we could compare the absolute magnitude to how bright it actually looks in the sky, being the apparent magnitude. If we compare them, we can calculate the distance. So this is a really powerful diagram. We can do a lot with it. It's incredible for comparing and understanding differences between stars. But if some piece of information is missing, we can back out what's missing based on the other information that we do have about that star. So here is a, I think, rather confusing way to look at this diagram. You can barely see what it says, but it just shows the size. So here we see our white dwarfs. They're teeny, teeny, tiny. They're really warm, but they're not very bright. Here we have our main sequence. And then we have the very large stars. So here are our supergiants way up there. They're off the page. They're not very hot, but they're huge, so they're still bright. So actually more than half of the stars are not alone. They are actually part of what we call a binary system. So that means that there are two stars that are orbiting each other. So they're orbiting around the center of mass of their system. They always lie sort of on a single plane. So let's say one star is the golf ball, one star is the tennis ball. So they're rotating around their center of mass, but they're always sort of on this flat plane together. So if you had a pair of binary stars that have different masses, for example, a tennis ball versus a golf ball, where would you expect the center of mass to be? So if one is larger in mass, one is more massive than the other one, where would the center of mass be? Because we know they're going to orbit around their center of mass. Would the center of mass be directly in between the two of them? No, because they don't have the same mass. The center of mass is going to be closer to the star with the higher mass, because it's the center of the total mass of the system. So the center of mass will be closer to the heavier, more massive star. So here we have, let's say we have star B here, star A here. So you'll see the center of mass is closer to star B because star B is more massive. So the line between, if you draw a line from star A to star B, it's always going to cross through the center of mass. You'll see that these two stars are rotating nice and perfectly around that center of mass. So more than half of the stars in the universe are actually in binary systems, locked in the system with another star. So there's two types of binary systems, and it's based on how we view them or how we determine that it is a binary system. So the first is a visual binary system. This just means we can see two stars, and we've determined they're rotating around each other. So when we can see two separate stars, I mean, they're going to be close together, but we can separately measure two stars, and we can see that the two stars are moving around the center of mass. We can actually create a little map of the orbit using our Doppler shift, blue shift versus red shift, to determine which star is moving towards us, which star is moving away from us. So we're going to have to map the orbit of these stars over many years to see the orbit. But when we can see two stars, we can use the Doppler shift to determine that they're moving in an orbit around each other. We call that a visual binary system. But it is not always this easy, of course, because we also have what are called spectroscopic binary systems. And this is when stars are too close together to actually be seen as two separate stars. So from our point of view, it just looks like one point of light. We can't actually see that it's two stars there. They're too close together. But what we can do is look at spectral lines over time to determine that you're looking at two different stars depending on the time. You're not looking at the same one star this whole time. So we can take spectral lines of that point of light at different times and see if there are changes. So if we had the same object, it's going to emit the same spectral lines, the same pattern all the time. It may shift, the pattern may shift, blue shift or red shift, but it's going to be the same exact pattern. When we see a change in pattern over time, when we see a switch, let's say at time 1 we see spectral lines like this, time 2 we see spectral lines like this, time 3 we see time 1 again, time 4 we see time 2, meaning it's switching back and forth between this very different pattern. This is not a shift, this is a totally different pattern. That means we're switching between two different stars. We're observing a binary system. They're so close together, we couldn't tell it was two separate objects. So what we're seeing at time 1 is the first star in front, or closer to us, so it's brighter. What we're seeing in time 2 is the second star in front, or closer to us, so it's brighter. So depending on where the stars are in their orbit, we might be looking at star 1 or star 2. So here's a little GIF. We see the highest brightness when the stars are together, because we're looking at a combination of both stars. But the brightness is actually going to dip when one star is blocking the other star. So they're sort of eclipsing each other. The brightness will dip because we're not seeing a combination of brightness anymore. We're only seeing the brightness of one star. So we can use this as well to see that there's a pattern of these double brightness dips. That means we're looking at two stars that are rotating around each other. So surveying stars is incredibly difficult. There are a lot of stars to look at. And as it happens, bright stars are very rare. Most of the stars in the sky are red dwarfs and white dwarfs. They're small, they are not bright, and we can't see most of them. So most of the stars that we see in the sky are the giants and the supergiants. When we look up at the sky, we're not seeing a real sample of the stars. We're only seeing the brightest stars, or the largest stars. We aren't seeing those red dwarfs and white dwarfs. We're not seeing all the most common stars. We're only seeing the very brightest. So if we look at this sort of three-dimensional HR diagram, you'll see the HR diagram is on the bottom, and it's just showing us the frequency of stars, so how many of each type of stars exist. So you'll see the red dwarfs, there's the most. So there's tons and tons and tons of red dwarfs, it's the most common. There also, the second common would be the white dwarf stars. So most of the stars in our sky are red dwarfs and white dwarfs. The main sequence stars, even the brightest of the main sequence, there are very, very few, to the point where it's not even on the graph. And it's the same with the supergiants and the giants. There's very, very few, even though these are the stars that we actually see when we look up at the sky. So, to add one more factor to our HR diagram is we can talk about star density. Now, this only works for main sequence stars. So, stars on the main sequence are ordered by mass. So the most massive stars are the hottest stars, the brightest stars. The least massive stars are the coolest stars. They're less mass. Outside of the main sequence, there is no order. So outside of the main sequence, we can't think about density or mass in any type of order because there is no order outside of the main sequence. Only the main sequence stars are in this nice order. So you'll see here for main sequence stars only, there's a really clear relationship between the mass and the luminosity. So as mass here on the x-axis goes up, luminosity also goes up. So all of the main sequence stars fit this equation where mass and luminosity increase together. So we can calculate density there from that. So most of the main sequence stars are actually going to have the same density because as their mass goes up, the volume goes up. So they're going to be similar density, these main sequence stars. Now, low density stars are going to be our giants and our supergiants. They are super low density because they are gigantic and they do not have as much mass for how big they are. So we're going to have giant stars with a very low density. Supergiant stars have an even lower density. Now, our high density stars are going to be the white dwarfs. So this is where the mass is generally about equal to that of the sun, but they are teeny, teeny, teeny tiny. So these stars are very small, but super, super massive. So they're going to be very high density stars. So the low density stars are the big guys, the giants. The high density stars are the white dwarfs, the teeny stars.